Okay, let's jump to number 4 on the calculations and go through how to calculate moles of solute particles in each solution. What's going to be of consequence here is whether our material, our solute, is, if we identify it as being an electrolyte or as a non-electrolyte. For all non-electrolytes, the I value is going to be equal to 1. Electrolytes, the I value depends on how many particles our ionic compound breaks apart into when it goes into solution. For example, if we had an ionic compound, potassium bromide, when potassium bromide goes into solution, it's going to break apart into potassium ions and bromide ions when it's in the water, and the I value for this would be equal to 2. If we had something else, say barium iodide, we'd find that barium iodide breaks into barium 2+, an iodide ion, and our I value would be equal to 3. In preparing each solution, now this will be an example with numbers different from the actual lab, but just to provide you an example similar to the lab. Let's say that for this set of data, the number of moles of solute for each group was 5.00 moles of solute. The number of moles of solute you would get from what your answer was for number 3 in the calculations. Now, whatever the moles of solute are, if the I value is equal to 1 for a non-electrolyte molecule, then the moles of solute particles would be 5.00 moles. However, if we had something like KBr, where our I value is equal to 2, we're going to have 5.00 moles of solute times 2 for the number of particles it breaks into, and we get 10.0 moles of particles that we form when this goes into solution. Similarly, for the barium iodide, if our I value is equal to 3, what happens is we have our 5 moles of solute that we weigh out. It breaks into 3 particles when it goes into solution. So what that creates is 15 moles of solute particles. Now, as you notice here, as we go from an I value of 1 to an I value of 2 to an I value of 3, even though we weighed out 5 moles in each scenario of the solute, because the number of particles that it breaks into increases, that changes the moles of solute particles that are in the solution. Now let's go through how you'd get moles of solvent. Hypothetically, again, this being an example, let's say that for purposes of our example, we had 500 grams of water was our solvent. Now we can use a proportion to solve for how many moles this would be. We know that 1 mole of water is 18 grams, so that means X moles of water would be present if we have a 500 gram sample. Solving for X gives us 27.78 moles of water as our solvent had we used 500 grams of water for our solvent in creating our solution. Now the next thing, number 6, asks us to calculate mole fraction of solute particles. This is just a fraction that we get by taking the moles of solute particles divided by the total moles. The total moles would be the combination of solute particles plus moles of solvent. Now if we use an example from our I equals 1 set of data, we had 5 moles of solute particles. That's our total solute particles. And then the total moles in the denominator, we have to combine the 5 moles of solute particles plus the 27.78 moles of solvent. Dividing this out gives us our mole fraction, or our fraction out of the total moles of particles, the fraction that's just the solute particles. We find that for this example, the mole fraction of solute particles would be 0.15. Now for the next one, when I equals 2, what happened is our moles of solute particles is now 10 instead of 5. So our numerator is 10 moles of solute particles. The denominator becomes 10 moles of solute particles plus the moles of solvent. Dividing this out, and we find that our mole fraction of solute particles is now increased to 0.26. Repeating the calculation for our I equals 3 solute, what happens is the moles of solute particles is now 15. Our moles of solvent remains at 27.78, and we find our mole fraction now increases to 0.35. To now go forward and calculate the mole fraction of solvent, we can use the same strategy in the previous problem, where if we just take now moles of solvent divided by the total moles of solute plus solvent, that'll give us the mole fraction of solvent. Or an alternative strategy, because all the mole fractions need to add up to equal 1, we can just take 1 minus the mole fraction of solute, and that'll give us the mole fraction of solvent. Either strategy will give us the same answer. Let's go through one each way. In the first strategy, we have our moles of solvent is still 27.78. That's our numerator. And the denominator is a 27.78 moles of solvent plus the 5 moles of solute particles that we have for our I equals 1 example. Divide this out and we get a mole fraction of 0.85 for our solvent. In the alternative strategy, we know that all of our mole fractions have to add up to equal 1, and we subtract from it the mole fraction that's the solute, and that'll give us the mole fraction of the solvent, which also comes out to be 0.85, using either strategy to calculate. To calculate the new vapor pressure for the solution compared to the vapor pressure of the pure solvent, we need to know what the vapor pressure of pure solvent is at some given temperature. Given that we know that water boils at 100 degrees Celsius, and that at this temperature the vapor pressure has to equal the pressure over the liquid, we know that the pressure of the vapor pressure at 100 degrees would be 1 atmosphere. This gives us our known vapor pressure at a known temperature for our solvent, which in this case is water. The equation that we'll use is the one that connects the vapor pressure of pure solvent, the mole fraction of solvent, and what the new vapor pressure of the solvent, of the particles of solvent that can become gaseous over the solution, to allow us to get the vapor pressure over the solution. Now, from our previous calculation, we found that for our solute, where I equals 1, the mole fraction was 0.15, and for our solute when I equals 2, the mole fraction of scratch that, fine chemists. What we found is the mole fraction for I equals 1 of solvent was 0.85, and for I equals 2, the mole fraction of solvent would be 0.74. Let's use these as samples for our calculation to give an example of how to do this. Our new pressure, P1, is going to be X1, which is the mole fraction of solvent. So we'd put in 0.85, and our pressure, in this case, vapor pressure of water at 100 degrees, which is our pure solvent, would be 1 atmosphere. Or we could do this in millimeters mercury. Either way will still give us a new vapor pressure. So P1, which is the vapor pressure of the solvent particles that could become gaseous over the solution, would now be 0.85 atmospheres. Repeating the calculation now for our solute when I equals 2, we now have that our mole fraction of solvent is 0.74. The vapor pressure of pure solvent is 1 atmosphere. So the pressure of our vapor pressure of the solvent particles that can become gaseous now over the solution would be only 0.4 or 0.74 atmospheres. Now, one thing we can see here is as the amount of solute particles is increasing, which causes the mole fraction of solvent to go down, the vapor pressure of the solvent over the solution is becoming less and less. The next calculation is just to find our change in vapor pressure comparing pure solvent to the solution vapor pressure. So we'd have 1 atmosphere. If we look, our pure solvent vapor pressure is the 1 atmosphere for water. We subtract from it the vapor pressure over the solution, and that gives us our change in vapor pressure. Now we notice that the change in vapor pressure gets greater as the amount of solute particles increases, causing the mole fraction of solvent to decrease. So the vapor pressure of the solvent becomes less and less as the mole fraction of solvent gets less. So we see a greater change in our vapor pressure. Jumping to calculation number 12, this is how we would go about calculating percent error. It'd be comparing our known minus the experimental divided by the known, and we take the absolute value to prevent us from getting a negative percentage, and then multiply by 100. That gives us our percent error. Let's run through a sample for number 14. This is how you can use the change in boiling point to actually find the molecular weight, or how many grams are in 1 mole of a non-electrolyte solute. We'll use this set of data to calculate and go through this example. The equation that we'll use is the change in temperature boiling is the boiling point constant Kb times the molality times I. Because this is a non-electrolyte, the I value will equal 1. This reduces our equation. The change in temperature boiling is Kb times m. The first step in solving this problem is we know our change in temperature boiling is 5.2 degrees Celsius. Our Kb value is 0.52. Is we can solve for the molality, small m. And we find that 10.0 is our molality, or small m. Now we also know that molality is measured in moles of solute per kilogram of solvent. This lets us set up this equation to solve for the moles of solute. We calculated and know that our molality is 10. We were given that we weighed out 500 grams, which would be 0.500 kilograms of solvent. What we don't know, though, is how many moles of solute we put into our solution. We know how many grams we used, but not how many moles. By taking the molality and setting it equal to X moles of solute over the amount of solvent we used, 0.500 kilograms, that will allow us to find how many moles of solute were dissolved to prepare this solution. Solving for X gives us 5.0 moles of solute were used in preparing this solution. Now our goal is trying to find the mass of 1 mole of this non-electrolyte. Molecular weight is measured in grams per mole. So there's 2 things we need to know to solve for this. We need to know grams and we need to know moles. By using a proportion, we have 260 grams of solute, which is the information we're provided. We know that that is now 5 moles of solute, so 260 grams are present in 5 moles, which means we'd have X grams present in 1 mole. Getting how many grams are in 1 mole will give us the molecular weight of our compound. X comes out to be 52, therefore our molecular weight is 52 grams per 1 mole for our non-electrolyte solute. The last calculation we have is a connection between mass percent and also parts per million, which is abbreviated ppm. Now mass percent is where we take the mass of the solute and divide it by the total mass of the solution, which would be the mass of the solute added together with the solvent. Our solute mass was 260 grams. Our solvent was 500. Combining the 260 and the 500 gives us the total mass of the solution. This gives us a mass percent of 34%. Mass percent is the same as parts per 100, meaning that if we had 100 grams, 34 grams of this would be solute, or 34 parts out of 100 are solute compared to the whole thing. So mass percent is the same as parts per 100. Parts per million is the same idea, except that it would be how many grams would be solute out of 1,000,000. To convert, we just have to take mass percent times 10 to the 4. Converting to parts per million, we find we have 340,000 parts per million based on our mass percent.